and sharing my screen so we can get started today. All right, so today we are going to be looking at a topic called limits analytically, as I said. When I say analytically in this context, another way I really could say this is algebraically. Meaning these are going to be the cases where we do not have the graph in front of us. We may not even know what the graph looks like. So we're going to have to rely on our algebra skills in order to find these limits. So this whole unit, as you know, is called limits. There's lots of different ways that we are going to be finding limits. And in my head, I like to think of a flow chart. So for these notes and really for like the next, today, Monday, Tuesday, and Wednesday, you might just want to have like a separate sheet of paper in your notes to do a flow chart, and just plan on taking up like the whole sheet of paper. So we're going to add things after these 4 boxes. But when you're asked to take a limit and you are dealing with it algebraically, the first thing you're always going to do is direct substitution. And by direct substitution, we're just going to plug it in. And when we plug it in, there's basically going to be 4 different things can happen. 2 of them I would consider like things you'll like to happen because it makes the problem easier. There's 2 other things that can happen which you'll be annoyed with because it usually requires some more work. So before I kind of tell you what's going to happen in the flow chart, I do want to just kind of see some examples first. So I've picked out a rational expression. I have f of x is equal to x minus 1 over x squared plus 2x minus 3. And I want you to find the limit of these by plugging in that value. And so what I mean by that is we are going to plug in 0, then plug in -3, and then plug in the 1. So go ahead and do that for me pretty quickly. You should notice like we get 3 different types of answers. Don't worry about like factoring anything right now. I just want you to just plug it in as written and then simplify your answer. So go ahead and try that for me. And so we can do direct substitution. When I plug in 0 into f of x, I end up with a 0 minus -1, which gives me -1. 0 plus 0 minus 3, which is -3, which we can, of course, reduce that as 1/3. This is a type of example you will like to get. When you have a real number answer, whether it's positive, negative, or the number 0, if you get a real number answer, you are done, and that is the answer to your limit. So this one, you plug in 0 into the function, you get out 1/3. The limit is 1/3. The second one, when you plug it in, you get -3 minus 1, which is -4. Over, we have 9 minus 6 minus 3, which ends up being 0. Does anyone remember what it means in math to have a number divided by 0?
Undefined.
Undefined.
Undefined. So this value right here is undefined. If the number is undefined, what do you think we're going to say about the limit?
It doesn't exist.
Does not exist. So if we get an undefined number, so basically we get a number over 0, the answer to our question will be D and E. And we're also happy about that case because it's easy. Number over 0 will always be undefined. This third one, I have 1 minus 1, which is 0. And then I have 1 plus 2 minus 3, which is also 0. I'm not going to ask you what 0 over 0 is in math because honestly, you'll probably get it wrong. 0 over 0 in math means absolutely nothing. It's not undefined. It's not 0. It's not 1. It's not anything. It is meaningless in terms of math. So this is going to be the case where you will not be happy because it means that you're going to have to do some work to get to the answer. For now, I'm just going to say keep going. And we'll go back and figure out what it means when I say keep going. But again, the short answer is once you see a limit and you have to evaluate it, always plug in a number first. So that brings me back to the flowchart. The first case that we have is when you plug something in, if you get a real number, that number is your answer. You are done. That is the answer to the problem. You don't have to do anything else. If you get a non-zero number divided by 0, we know that's undefined. You're also done because the limit is going to be D and E. These bottom two boxes are going to be for the cases where we have to keep going. And the cases that happen when we have to keep going, I'm going to write that in both what I have, the orange and the yellow box. In the yellow one, I am going to go ahead and put that 0 over 0. That means nothing in math. I'm going to add a second one in here too while we're at it. We're not going to cover these until Tuesday, but I'm going to add infinity over infinity. That's also something that's meaningless technically in math. And then in the orange one, I'm going to add infinity minus infinity. That may not make a lot of sense right now, and in fact, it really shouldn't, but that's just kind of the 4 cases that we have with limits in this class. And so when you have a real number, you're good to go. When you have a non-zero number over 0, you're good to go because you know it's D and E. Whenever you have things like 0 over 0 or infinity over infinity, then we're going to have to keep doing something else. So let's talk about that. Like, what do we mean by saying 0 over 0 or infinity over infinity? So let's just think about some basics that we have in math. I have, well, it's 8 things, but one of them I repeated, so I'm going to cross it off and pretend like it's not there. So we have 7 things that I do want to kind of talk about and make sure that we know, like, what it means. Some of it's pretty basic, some of it gets a little bit more theoretical. I'm going to start with the red column first, because we're going to see a lot of fractions when we do limits. So in this first one, if I have 0 over anything, in math, what is 0 divided by anything?
0.
0.
0. 0 divided by 4, 0 divided by 5, 0 divided by negative 100. It's all 0. Good to know for that. Underneath that, we already kind of answered it. If I have anything divided by 0, what do we say that is?
Undefined.
Undefined. What about anything divided by itself in math? What does that equal?
1.
1. You're like, Ms. Around, this is pretty basic stuff. And I'm like, yeah, but you know it's probably not going to stay this basic. And then we have this 0 over 0. So the official phrase we're going to use for something like 0 over 0 is called an indeterminate form. I'm going to write it in blue because my board's not working there. Indeterminate form. Because you basically can't determine what it is. And in math, we actually have lots of indeterminate forms. 0 over 0 is definitely one of them. Infinity over infinity is another one. There are some that exist that we won't cover in this class, like 1 to the infiniteth power is indeterminate. and things like that. But 0 over 0 is the most common one we'll see. So let's move over to this blue column and let's talk about what it means when we're dealing with infinities. So first off, let's talk about infinity. What do I mean when I say infinity? What is infinity?
Never ends.
It never ends. So it is just a big old number. It is just a huge, huge, huge number. It never ends. And in calculus, we deal with this idea of infinities a lot. And we're going to drift into some like theoretical area, which for some people it blows their mind for a little bit. But whenever I think of infinity, I just kind of think of that as like the biggest number I can imagine. So we first want to talk about like if I just have infinity, this massive number divided by anything. Well, what do you think infinity divided by anything is going to end up being?
Indeterminate.
It's not going to be indeterminate. We can still describe it as something. So I'll think about it this way. If you have infinity goes on forever and you divide it by 2, how much do you still kind of technically have?
Infinity.
Infinity. Like you can't break it down. It's still always going to be infinity. So we're going to say that infinity divided by anything is always going to approach infinity. You can't get infinity any smaller. It is always going to be infinity. Let's think about when we flip that fraction around. If I have something and I just start dividing it by really, really, really big numbers. So I might think of fractions like 1 divided by 10, 1 divided by 100, 1 divided by 1,000, 1 divided by 1,000,000. What is that approaching if I start saying anything divided by 0?
0.
I just said the answer. Let me ask that question better again. Yeah. What is anything divided by infinity?
0.
0, yeah, because I said the answer. But let's make sure we're kind of clear on that. So when I say something divided by infinity, we know when we have fractions, the bigger the number in the denominator, the smaller the fraction. For example, like if I have 1/2, we all know that's 0.5. If I have 1 over 20, we're getting closer and closer to 0. 1 over 200, even smaller. 1 over 2,000, even smaller than that. And we can kind of just keep adding zeros. We'll never be able to get to infinity because that's kind of the idea of infinity. But if we have something divided by infinity, we can say that that is basically 0. And then that does bring us to this last one I have on here, infinity over infinity. So that looks like the case where we say anything over itself is 1. But infinity divided by infinity is not always 1. And so here's us going into some weird theory land. So infinity does mean it goes on forever and ever. But in math, we have some infinities that are bigger than other infinities. For example, if I go out forever for an exponential function, that's going to be a whole lot bigger than if I go out forever on a linear function. So when we just say infinity over infinity without any context, we don't know if that's like a big infinity or an even bigger infinity. And it's kind of weird to discuss infinity in all these vague terms. But we'll see, especially next week when we do limits intuitively, it's going to help us to be able to imagine like what infinity is and kind of what happens when we divide by it or divide things by infinity by a number. So that does bring me back to the flowchart. And so when I'm doing the flowchart like this, and I have, we get the real number, that's the answer. A number divided by 0, we're going to say the limit does not exist. If we have 0 over 0 or infinity over infinity, we're going to keep going. What we're going to look at today is called just algebra. And when I'm looking at a limit, there's really 3 main things I look for when I want to solve a limit algebraically. The first and most obvious thing I kind of look for is I'm going to see if I can factor and cancel. Usually I have something like polynomials if I can factor and cancel. The next thing I try to do is to rationalize.
Should we write this down?
I would, yeah. The next thing I would try to do is rationalize. And I will say we will tend to rationalize if you see a square root in the problem. Or it could be like a cube root or fifth root. But if you see some sort of root, I would definitely rationalize the example. And then the third, this is going to be ones you're annoyed with, because I'm just going to leave it vague at just any other algebra you can do. And that's one thing about limits is like you can't mess up as long as you're following proper algebra rules. So maybe you get like a common denominator, or maybe you factor it, or maybe you find a way to rewrite it using exponents. But as long as you're using properties of algebra and using them correctly, you can't really mess up limits. And the idea behind this is you want to be able to do something to simplify it so that direct substitution works out. Because the goal is we don't want to have 0 over 0. We want to either have a number over 0 or we want to have a real numbered answer, because 0 over 0 is something that is indeterminate. Questions so far? All right, so I'm going to go back and look at this example. So that third one was the case that we had 0 over 0, and it was the case that we could keep going. So I've copied that problem down again, and I want to try to do it now by factor and cancel using the methods that we have. So for factor and cancel examples, I have the limit as x goes to 1 of x minus 1 over x squared plus 2x minus 3. Now we already did this one, but please don't waste your time. Always check by doing direct sub, because if you don't get 0 over 0, then you're going to waste your time by trying to do a whole bunch of other stuff. We already looked at this one. We know that it is 0 over 0. So I'm going to go ahead and try to factor and cancel. So I'm going to write this LIM as x goes to 1 over again. In calculus, especially with this being an AP class and having free response questions, we want to make sure that our math notation is correct. So do not stop writing the LIM part until you plug in the value. So we're going to write LIM over and over and over again until we're able to plug in 1 for x. So looking at this problem, let's go ahead and try to factor it. So x minus 1, that's good to go as is. So I have x minus 1. This denominator, I am going to go ahead and factor. It is a trinomial, so I can factor it. I have x and x, and it looks like it's going to be a 1 and a 3 minus and plus. One clue I'll tell you, like if you get 0 over 0, you should have something cancel out. If you don't have anything cancel out, then you've done something incorrectly. So looking at this, I have factored. We see some factors that cancel out. The x minus 1s have canceled out. So this new problem becomes the limit as x goes to 1. We just have a 1 left over on top, and then we had an x plus 3 left over in the bottom. Are we able to do direct substitution now?
Yes.
Yes, so when we plug it in, we're plugging in 1 for x, so I have 1 over 1 plus 3. Notice now I dropped writing the limit because I was able to plug it in, which is just equal to 1/4. So the answer to this limit was not 0 over 0. We factored, we canceled, and now we know that the limit is 1/4. Well, what does this mean? Let's kind of think back to some prereq skills. When I canceled out that x minus 1, what feature is there actually happening in the graph right there?
A hole.
Well,
It's a hole. So basically, if you want to think about it, you're canceling out the hole in the graph. And so if you were to graph this one, and again, this is why algebra is nice, because you don't have to know what it looks like. I do, because I've been doing this problem forever. But this graph looks something like this. But at x equals 1, it has a hole. And where's that hole located at? It's located at 1, 1/4. But we were able to answer the question of that limit without having the graph in front of us because we can trust our algebra. We canceled out the hole, We've eliminated the possibility of getting 0 over 0 and then just plugged it in using direct substitution. Questions or concerns there? All right, so there's my flow chart. We know that once we try something, we always want to go back and try direct substitution. So that was an example of factor and cancel. Let's look at another example. So sometimes we factor and cancel, sometimes we want to rationalize. So let's look at a rationalizing example. So I have the limit as x is going to 4 of 4 minus x over 2 minus the square root of x. So first thing you always want to do when you're solving a limit problem is what? What's the first thing you should always attempt to do?
Plug it in.
Plug it in, because there's no point in doing anything else if you haven't plugged it in. Now, hopefully you can do that in your head. I'm going to draw like a little thought bubble, because this is happening inside my head. But I can see that 4 minus 4 over 2 minus the square root of 4, that is going to give me 0 over 0. We know when we're doing limits, if we have 0 over 0, we have to keep going. So right now, our options for keep going is just algebra. Looking at this, we can't really factor it. There's nothing to factor. I do see a square root, and the square root, when you see one, is always your big clue that you're going to rationalize. What do I mean by rationalizing?
Multiply by the square root over the square root so that you get rid of the square root in the bottom.
So we want to get rid of the square root of the bottom. This one has more than just a square root in the bottom, so I can't just multiply by the square root of x. What am I going to need to multiply by?
The conjugate.
The conjugate. So I have 2 plus the square root of x, but this is a fraction, so what I do on the bottom, I also need to do up top. And I do want to make one thing clear. Probably up until this point, you've only rationalized the denominator. Technically, you can also rationalize the numerator. The word rationalizing just means getting rid of the square root wherever it's at. And so this is a process that will basically, if you do it correctly, something should cancel out. And so I do want to give you some tips and hints when it comes to multiplying this together. We are going to have to use FOIL. Again, I'm going to go ahead and write LIM x goes to 4. The first hint I will tell you, and it will save you a lot of time, is the part of the fraction that did not originally have the square root, don't FOIL those together. So what I mean by that is this numerator did not originally have a square root, so I'm going to go ahead and bring those straight across. And the reason why is you're going to hope that something in the denominator can eventually cancel with the numerator. So let's go ahead and FOIL these together. First, outer, inner, last. So when I do first, 2 times 2, that's going to give me 4. The outer, 2 times the square root of x. The inner is negative 2 square root of x. And then last, I have a negative times a positive. So negative square root of x times the square root of x is just x. If you do it correctly, those middle terms will always cancel. You wouldn't even have to write them down because I think most of us know that they would cancel. But we do end up with this expression, the limit as x goes to 4, of my numerator, 4 minus x, 2 plus the square root of x. All over, I was just left with a 4 minus x. Do we have things that cancel out? Yep, 4 minus x cancels. Now we can go ahead and do direct substitution. So I have 2 plus the square root of 4, 2 plus 2, which is 4. Some things I want to say about this problem, and then I'll take some questions. So this one is a hole. This graph, I definitely don't know what it looks like, but I do know that there is a hole in the graph at 4, 4. Sometimes when you get to this step that I just drew an arrow to and an asterisk, sometimes you don't have things that cancel out immediately. Sometimes you have to go back and maybe like factor a number out or factor a negative out, and we'll see some examples like that on Monday. But basically the goal is you need to cancel something. Basically you're canceling out the 0 over 0 so that you can plug in the limit. Any questions on this problem?
How come you don't do like the plus and minus, like to get
Good
to the
question.
answer?
There is a square root here, but I'm not doing the plus or minus because I am not solving the equation. So you only do plus or minus square root when you take the square root, like the verb taking the square root. The square root is just in the problem, so we're just using the primary root as it's written. So I'm not solving for x or anything, so there's no plus or minus in the problem. If that makes sense. Any other questions?
No.
All right, next one I want to do is this one. So looking at this particular problem, I have f of x is equal to a piecewise function. So I have this piecewise function of 3x minus 1 for when x is less than 2. And I also have f of x is equal to x squared minus 3 for when x is greater than or equal to 2. Just as a quick refresher, a piecewise function basically pieces together different functions together. This first portion, 3 minus 1, is only existing when x is less than 2. The x squared minus 3 is only existing when x is greater than or equal to 2. So before we do the limits, let's review and talk about how we would do the value. If I just wanted you to find what is f of 0, which piece of the function would you end up using?
The top one.
The top one. 0 is less than 2, so you would have to end up using the top one to get negative 1. Likewise, if I wanted to find f of 10, 10 is bigger than 2, so I would end up using the bottom one. So I would have 10 squared minus 3, or 97. What if I had the value at f of 2? Which one would I use?
The bottom one.
Bottom.
The bottom one. So which one is including the 2? The bottom one. So 2 squared minus 3, 4 minus 3 is 1. So that was like pre-calculus stuff. Now we're looking at calculus level stuff. The limits, we still have to kind of think about the piecewise. This first one, I have the limit as x is going to 2 from the left. So if I'm coming at to 2 from the left-hand side, we already saw that 2 is kind of the border between these two pieces. But which function would be considered to be immediately on the left-hand side of 2?
The top.
The top one. So it is an open circle, but it doesn't matter. We're still going to use the left-hand side. So I would have the 3 times the 2 minus the 1, or 6 minus 1, which is 5. Likewise, if I want to find the limit as x goes to 2 from the right, that's coming in from the positive side of 2, so I would use the second one. So I would have 2 squared minus 3, 4 minus 3, which gives me 1. So then the main idea kind of for limits, if I just want to find the limit as x goes to 2 overall, technically, which piece of the piecewise will I need to use?
Doesn't it
Or,
Oh,
say it
the
again.
bottom?
doesn't it not exist?
It is, so we kind of using the bottom one, but I would also agree more with does not exist. How do we know that the limit as x goes to 2 does not exist?
Because it's a piecewise function.
It is a
There's nothing.
piecewise function.
They're
But
not
we could
going
have
towards the
piecewise
same
functions
thing.
that join up together. How do we know that this limit does not exist based off of what we've already found?
They're going towards two different numbers.
they're going towards two different numbers. So remember, I'm going to rewrite it next to it. We now know because of both of these we already did that the limit as x goes to 2 does not exist. Because even though it's a piecewise, we don't have to know how to graph piecewise. Sure, it's great if we do, but we know it does not exist because the limit from the left of 2 is not equal to the limit when you're coming in from the right side of 2. So this limit does not exist. If I wanted to graph this one, like I'm not going to do a perfect graph, but we basically have 3x minus 1, which would be a line. And there's a hole located at 2 comma 5. And then the other piece is a quadratic at 2. And it's included, but it's starting at 1 and forming a quadratic. So if you have the graph in front of you, it would be very obvious, oh, the limit does not exist. But without the graph, we were able to check the left-hand side and the right-hand side and kind of see what it looked like from there. Questions or concerns about the piecewise?
No.
No, all right. I know it's Friday, I'm gonna give you one more, and then I'm just gonna stop there and we'll do the rest on Monday. I'm gonna pick out one I like. Try this one. So again, you know, your first step is to always try to do direct substitution. If that doesn't work, right now our only options are pretty much factor, rationalize, or perhaps some other algebra. And if you get stuck on this one, I might just say SOAP, and it might jog your memory of what you need to do. And there's the SOAP factoring pattern if you need a reminder of it. So if I'm looking at this problem, I'm finding the limit as x goes to 4. Always try to plug in 4 first, but this one, 4 cubed minus 64 is 0. 4 minus 4 is 0. We get the indeterminate case, so we need to keep going. Looking at these are polynomials, so factoring kind of makes sense. So I have x and 4, x, 4x, and 16. Same sign, opposite sign, always positive. Again, if you do these problems correctly, if you have 0 over 0, something should cancel out eventually. So we see that the x minus 4s do cancel out. So now we are able to plug in our 4. So plugging in 4, we get 4 squared plus 4 times 4 plus 16. And honestly, you can leave your answer like that for me. I'd rather you have a correct answer than you simplify an answer and get it incorrectly. Or of course, you could just add those all together and you would get 48. But both of them are acceptable. Questions on that? All right, so we'll pick up these notes tomorrow. Continue working on homework 1 and homework 2. I will say if you're feeling ahead, homework 2 is posted, of course, already. I did update it where I only want you to do the even numbered problems. Like the answer key has all of them worked out, so if you want to do all of them for extra practice, that is perfectly fine. But I'd rather you, I just don't want you to get overloaded with work in this virtual environment. So homework 2, if you are starting it, I'm only requiring the evens. Do just want to remind you, of course, you have about 8 minutes to submit your prereq assignment if you haven't already. And then other homework assignments you have to be working on are homework 1 and homework 2. Someone asked me again, when was homework due? Excluding homework 0, again, I only check homework on quiz days and test days. So homeworks 1, 2, and 3 are going to be due on Friday. And there won't be any other assignments between now and Friday. So there's just one more assignment, and you'll know what it is on Tuesday. So then you pretty much have a whole week to get 1, 2, and 3 done. So that's all I have to say for you. I'm going to go ahead and pause it pause the recording.